Welcome to lecture 10 of module 3 of the course Game Theory and Economics. So, what we have been discussing in this course, in this module so far is that we have been taking up different applications of Nash equilibrium, and the current application that we have been discussing is the case of war of attrition, where there are two parties and they are fighting with each other over certain object, maybe a prey. Two hunters might be fighting over a prey, and the more they continue to fight, it is worse for both of them. They are inflicting damages on each other. So, the earlier my rival gives up, it is better for me, then I get the object, but my payoff from getting the object will definitely depend on how much time he has spent in fighting with me. So, this is the setting, and we have found that the main result of this framework is that in the Nash equilibrium there will be an asymmetry, in the sense that one player will give up immediately without fighting, without spending any time in fighting with the rival, and the rival will get the object, and vice versa, in the sense that the rival can give up at the beginning itself, and the first player can get the object without fighting. So, both sets of Nash equilibria are possible. Today we shall go further and look at different aspects of this same setting. So, one exercise that we want to do, a real life application, is the following. Two firms are developing competing products for a market of fixed size. The longer a firm spends on development, the better its product. But the first firm to release its product has an advantage. The customers it obtains will not subsequently switch to its rival. A firm that releases its product first at time t captures the share Ht of the market, where H is a function that increases from 0 to time capital T, with H0 is equal to 0 and H of capital T is equal to 1. The remaining market share is left for the other firm. If the firms release their products at the same time, each obtains half of the market. Each firm wishes to obtain the highest possible market share. Model this situation as a strategic game and find its Nash equilibrium or equilibrium. So, in a nutshell, what is happening is that there are two firms. These are the players, set of players. What are the actions that they are undertaking? They are deciding what time they will spend in developing a product, and if I develop a product and release my product before my rival, then the time that I have spent in developing the product before releasing the product into the market, that will affect my market share. In particular, if I spend t time to develop the product and release it before my rival, then I get Ht of the market share. So, T is something which I shall decide on. So, in particular, T can be of can take two values, T1 and T2. T1 is the time that firm 1 has decided it will spend on developing the product. T2 is the time that the firm 2 decides to develop on the product. So, T1 and T2 are the then decision variables. Actions T1, T2, they are the time spent by firms 1 and 2 respectively in developing the product. What is the range of t? T can take any value between 0 but not infinity, but capital T. So, there is a maximum till which one can spend in developing the product, which is given by capital C. And if I, as I have said, if I spend t amount of time in developing the product, I get Ht share of the market, provided my t is less than the t of the other firm. And so, if I get Ht fraction of the market, my rival gets 1 minus Ht fraction of the market, and each firm tries to maximize the share of the market, because if you remember, what is being said is that the each firm wishes to obtain the highest possible market share. So, my aim will be to maximize H, that is the portion of the market that I am getting. So, that is the game. Each of two people has 1 unit of resource. Each person chooses how much of the resource to use in fighting the other individual and how much to use productively. If each person devotes yi to fighting, then the total output is yi f of y1 f y2, which is greater than equal to 0, and person I obtains the fraction pi of y1 y2 of the output, where pi y1 y2 is equal to 1 if y I is greater than yj, is equal to half if yi is equal to yj, is equal to 0 if yi is less than yj. The function f is continuous and decreasing in both y1 and y2 and satisfies f of 1 1 is equal to 0. Each person cares only about the amount of output she receives and prefers to receive as much as possible. Specify this situation as strategic game and find its Nash equilibrium or equilibrium. There are two players. And they are fighting with each other, and they are devoting y1 and y2 of resources to fight with each other. So, this is their actions y1, y2. They can take the value between 0 and 1, and highest. So, the highest value for y1 is 1, the lowest value is 0, same for y2. When they fight with each other and devote this y1 and y2, obviously they will be left with less y's or resources that they had to begin with. So, the total output that they will get if they devote y1 and y2 is given by f of y1 y2, where f is decreasing in y1 y2. So, more you spend in fighting with your enemy, you are left with less output, and so the total output, which could be a result of the resources of both the people, will go down. And the point is that even if I win, that is, even if I get the total output f, it may happen that I do not get the entire thing but a part of it depending on y1 and y2. So, in particular I gets Pi of f, where Pi is given by 1 if yi is greater than yj, half So, in short, if I have spent more resources than my rival, I get the full of this, the entire thing. If my spending of resource is equal to his spending of resource, I get half of this f, and if I am spending less resource than my rival, then I am not getting any part of this f. So, in other words, ui is equal to f of y1 y2 So, this is how it looks like. The question is which are the Nash equilibria. So, this is what the players want to maximize. They want to maximize this u, keeping in mind that if y1 and y2 go on rising, this f goes on declining. So, they will like to choose as little y as possible. Now, what are the Nash equilibria here? So, one exercise that we shall do about war of attrition is the following. So, this is the question. Suppose two firms are fighting over market share. Higher spending on advertisement by a firm raises its share and total profit. Total profit is denoted by SI. SI is a function of EI, where EI is the advertisement expenditure by firm I. Highest value of SI is 1. So, this is a normalized value. Lowest is 0. So, S varies between 0 and 1. If a firm spends more than its rival, it gets the entire market. The rival gets nothing. There is a law that EI cannot exceed half and it is greater than 0. Model this situation as a strategic game and find the Nash equilibrium or equilibria. Is there a different pair of E1, E2 giving firms higher payoff? One more point. If market share and profit. If E1 is equal to, each gets half of the market share and profit. So, we have to model this situation as a game, strategic game. So, who are the players here? The players are the two firms, firm 1 and firm 2. Okay. Actions. What are the actions that they choose? EI, and EI is greater than 0, it can be equal to 0 also, and EI is less than equal to half. Okay. EI is the advertisement expenditure. Just a moment, this is greater than equal to 0. All right. And payoff. So, UI is the payoff of firm I. It is a function of two variables E1, E2. I can be 1 or 2. It is equal to S of EI, sorry, if it spends more than the other firm, it gets the entire market, which means it gets 1 minus EI if EI is greater than EJ, and it is half minus EI if EI is equal to EJ, and it is equal to minus EI if EI is less than EJ. Remember, the total market that is there, the market share that is possible, the highest market share that is possible is 1. So, if my advertisement expenditure is more than the other firm's advertisement expenditure, I get the entire market, the highest value of S in that case is 1. And if our spendings are same, I get half of the entire market. So, that basically is normalized to half. So, this becomes the payoff function of each player. We have to find out what is the Nash equilibrium. For that, I have to find out what is the best response function. Of firm I, say. So, it is a function of EJ and it is given by what? Remember, the highest value that EJ can take is half and the lowest value that it can take is 0. So, always the firm I we like to have his expenditure slightly higher than the other firm's expenditure, and in doing so it will have like to have an expenditure greater than E j, but by how much? There is no any unique E I which is greater than E j, but lowest among all the possible values that it can take. So, therefore, it is given by this null set. If E j is less than half, right. So, this is one case. If E j is less than half, if E j is equal to half, then what happens? If E j is equal to half, remember in that case E I cannot be more than E j, because the highest value that E's can take is half. So, what player I can do in this case is make his expenditure equal to E j. In that case, he is getting what? If E I is equal to half, then he is getting half minus half is equal to 0, or he can spend 0, in which case his payoff remains 0. So, these are the two possibilities that he can do. So, in this case E I can be equal to half or 0, both giving I 0 payoff. So, in this case what we are having is this. So, this is the case. These are the best response functions. Let us now plot the two best response functions and try to find out what is the Nash equilibrium. So, here you have E 1 and E 2, and let us say these are the values half and half. We have seen that if E 2 is less than half, then there is no best response for firm 1. So, for this range there is no best response. If E 2 is equal to half, then E 1, the best E 1 could be either 0 or half. So, this is one possibility and this is another possibility. Both are equally good. So, this is B 1. What about B 2? We have seen that if E 1 is less than half, then there is no best response for firm 2, but if E 1 is equal to half, this is one possibility that E 2 becomes 0 or E 2 becomes half. So, this is B 2, B 1 as a function of E 2 and B 2 as a function of E 1. Therefore, the plotting the best responses So, this is the Nash equilibrium. This is the unique Nash equilibrium. Interestingly, the payoff of the two players are 0. Because both are choosing their highest possible advertisement expenditures, and the market is getting shared, and the payoff is becoming half minus half, therefore 0. Is there any other pair which gives the players better payoff than the Nash equilibrium payoff? Is there a different pair E1, E2 giving the firms higher payoff? It appears that there is at least one pair. If E1 is equal to E2 is equal to 0, the payoffs are, again the market is getting divided here, half and half, which is better than, which are better than 0 0. So, there is at least one better pair of actions. So, that is it. What we are going to take up now is another application of Nash equilibrium, which is known as the auction. So, what does auction mean? Auction basically is a problem of allocating of some precious resource among contending parties. So, this precious resource can be anything. It can be an object of art, it can be oil field, it can be mobile frequency, it can be radio frequency also. So, all these things are sold by the government or by the person who is owning it, not necessarily the owner always, to people who want to have that object. The people who are wanting to have the object obviously will compete with each other and try to outdo each other by announcing high and high prices. This quotation of the prices are known as bids. So, we say bidders, people who are submitting bid are called bidders, they are quoting prices. But as we shall see, the price that I quote for that object is not necessarily the price that I pay. There are different kinds of auctions. In some auctions you pay the price that you quote, in some case you pay the price which has been quoted by someone else. But nevertheless, the person who is quoting the highest price will generally get the object. So, that is the idea. Now, suppose there are suppose there are n people or n bidders. Now, there are two sets of things to remember here. Each bidder will have some valuation for the object, and it is not necessary that the valuation of any particular bidder will be same as the valuation of any other bidder. These valuations can differ across the bidders. So, we shall call these valuations as V. In particular, Vi is the valuation of bidder I for the object. Now, this is one set of variables that we shall remember, that is V1, V2, Vn. There is another set of values that one needs to remember. These are the bids. So, bids are B1, B2, Bn. This is the symbol that we are going to use for the prices that are quoted by each of the bidders. So, bidder 1 is having a valuation 1, and bidding B1, bidder 2 has a valuation of V2 and bidding B2, like that. Our task in study of auction theory, incidentally auction theory is a separate branch within economics, is to see in different kinds of auctions, is the allocation of the object efficient? Is it the case that the person who values the object most is getting the object, or does it can it go to someone else? We also want to look at whether the person who is conducting the entire thing, who is known as the auctioneer, is getting the maximum possible revenue from the entire bidding process. So, does it maximize the revenue? So, these are some of the questions that we shall be interested in, and we shall like to answer those questions. Now, as I just said that there are different kinds of auctions. The first kind of auction that we shall deal with is known as a second price sealed bid auction. So, think of the general idea of auction that we have. There are many people who have valuations for this object V1, V2, etc. And we are going to assume that these V1 and V2 are known to everyone. So, it is a common knowledge how I value the object, and I also know what are the valuations any other players possess for that object. Now, in general auctions, the auctions that we are familiar with, price starts from a very low value and it goes up. Now, if it goes up, then I can imagine that any person, any bidder will have a maximal amount of bidding beyond which he or she will not go. So, if that is the case, then ultimately the auction is a fight between two people. If I think that their maximals are different, maximal bidding that each person will submit is different from others, then it is a fight between two people, two highest maximal bidders. Okay. Now, if that is the case, and suppose B1 is greater than B2, that is player 1, the maximum amount that he is ready to pay is B1 and the maximum bidding that player 2 will do is B2, then what is the optimal bidding for player 1? In this case, observe that player 1 will not optimally bid B1, rather he will bid something B2 plus suppose epsilon, because if he is bidding more than player 2, he is getting the object. So, there is no point why he should bid B1, and B epsilon can be taken to 0, it can approach 0, which means that player 1's optimal bidding can be thought to be equal to B2 itself. He will not bid his own maximal thing. So, this is the idea, the general idea of auction that we have, and this is sought to be replicated in kind of sealed bid auction, where people do not observe other people's bidding. I do not see what the other people is doing. I do whatever I do, I submit whatever my maximal bid is, but if my bid is the maximal, suppose my B1 is the highest, then I will get the object, but the price that I will pay is not this B1, but this B2. So, by this technique of sealed bid, what we want to do is to replicate the original auction that we are talking about, where people can see each other's bids, but here people cannot see each other bids. Nevertheless, the auctioneer, when he receives all these bids from people, from the players, he picks up the bid which is the highest and decides that this player who has submitted the highest bid will get the object, but he will not pay the price that he has bid. He will pay the price of the highest of the other players other than him, and that is why it is called second price auction, not the first price, but the second price. And it is sealed bid, that I do not know what is the price submitted by other players, what is the bid submitted by other players, that is why it is sealed bid. And it is important that it is sealed bid, because if you remember, in this strategic game I do not know the action taken by any other player. So, it has to be a sealed bid auction. So, this is the rule of the game. Now, if I want to write this in terms of the language of game theory, the language that we have introduced so far, then I have to specify 3 elements. So, the players, who are the players? The players are the bidders, and they are n in number. N can be any value between, it can be any value which, as long as it is greater than or equal to 2. There cannot be any auction if there is just one player, one bidder to get the object. Action. So, what are they trying to, what are they deciding on? So, it is set of bids, all right, which is any non-negative number. So, BI is being determined by player I. Finally, preferences. Okay. Now, in general, let us write what is the payoff of player I. Player I will get the object under 2 circumstances. One is that his bid, that is BI, is higher than any other bid. All the other players are bidding something which is less than his bid. Now, that is one possibility, but what happens if there are 2 people who have bid the highest bids? For example, it may happen that BI, which is the bid of player I, is equal to B1 or suppose B7, then who gets the object? So, this is a case of tie, and we will follow the rule of tie breaking, that if B7 is equal to B10, suppose, that is the bid of player 7 is equal to bid of player 10, and this is the highest, then 7 will get it. Why 7 will get it? Because 7 is less than 10. And what is the rationale for that? Why are we assuming that the player with the lower number is getting the object? The reason is that, or the kind of rationale is that, we are going to assume that V1 is strictly greater than V2, etc., etc. Vn and Vn is strictly greater than 0, which means that player 1 values the object most, player 2's valuation for the object is less, etc., etc. The least valuation for the object is for player n, but which is still greater than 0. And these are different numbers, that also has to be remembered. So, in a case where bid of two players are equal, then the object is being allocated to person with the lower number, because that person values the object more than the other person. So, that is the rationale for this, rationale for tie breaking. Now, so player I will get the object then under two circumstances. One is B I is greater than every other bid, then player I will get it, and player I can get the object if suppose B I is equal to some other B, but I is less than the number or the index of that other B. In these two cases I will get the object. If I gets the object, then what is his payoff? Let us try to write that. So, it is written as V I minus B bar, where B bar is the bid of the highest bid So, and this will happen if B I is greater than B bar, or number of people who submitted B bar, numbers of people, let us say, because there might be more than one person who has submitted B bar, numbers of people who submitted B bar are greater than I. So, under these two circumstances, player Y will get V I minus B bar. One is when his bid is the highest, single highest bid, then he will get the object obviously, and the price that he pays is the bid of the people who, of the person who has bid the highest bid among the set of other players. So, his payoff in that case is the valuation of his for the object minus the price that he is paying, that is B bar. He can get the object also if his bid is same as some other people's bid and both these bids are highest and his number is less than the number of the other person. In other cases, UI is simply equal to 0. What can be the other cases? That BI is less than B bar, that is one case, or BI is equal to B bar, but I is greater than the number of the people who have submitted B bar. In those cases, outrightly we can say that UI is equal to 0. Notice it is not necessarily that this value V I minus B bar is positive. It may happen that this value is 0, this may turn out to be negative also, because it may happen a person has a low V, but has submitted a very high B bar, BI. So, bid can be in theory can be higher than your valuation. In that case it may happen that you win the object, but the payoff that you get is negative, or it can be 0. So, this is the general setting. We shall stop here. We shall try to see what are the Nash equilibria which can be derived in the case of second price sealed bid auction. So, before we finish this lecture, let me take you through what we have discussed in this lecture. We have ended the discussion of war of attrition. We have looked at the various aspects of war of attrition, but the simple thing that has to be highlighted is that in equilibrium, in the original model of war of attrition, people take different kinds of action. In particular, one person just withdraws from the fight immediately. There is no fight in equilibrium, but we have seen that there can be variations where in the equilibrium there are fights. For example, in the last case that we have seen, people fight for a long time in fact, and we have started the discussion of auctions, and we have started the discussion of particularly second price sale bid auction. See you in the next class. Thank you. In the product release game, when the time of release is same, suppose firm 1 gets the entire market, and then what is the equilibrium in this case? So, let us try to remember what was the product release game and what was the equilibrium. So, there are two firms which are planning to launch a product. If I launch earlier, so if I launch at this time T1 suppose, I get this much share of the market, but longer I wait for the product to develop in my research, I will get a bigger share of the market. So, more higher T I choose, greater share of the market I get. But there is a problem that if I wait for a long time, the other firm can launch his product earlier than mine and get part of the market, and I will be left with the rest of the market. The equilibrium we saw was the following. It was given by T star, where H T star equal to half, which means that they will release their goods at the same time T star. And what is the property of this T star? At T star, a firm, if it launches its goods at T star, it gets half of the market. This half represents that share of the market. Now, this was the case where if the time is the same, then market is shared in equal parts. Here, if T1 is equal to T2, then 1 gets the entire market. Question is, what is the equilibrium? Our claim is that there is no equilibrium here. And what is the reason? Reason is that if T1 is equal to T2, then 2 will have profitable deviation. Remember, at T1 is equal to T2, the market is equally shared. The market entirely goes to firm 1. So, the firm 2 will choose a time which is less than T1 and will get some portion of the market, does not matter what, but it will get some positive portion of the market. So, deviation by 2 is profitable. Now, this cannot happen if T1 plus T2 is equal to 0, then firm 2 cannot fix a time less than T1 which is equal to 0. So, in that case firm 2 will choose a time just little bit above T1, so that if T1 chooses 0, it gets 0 portion of the market, so that the rest of the market goes to firm 2. So, if T1 is equal to T2, there cannot be an equilibrium. If T1 is not equal to T2, that cannot be an equilibrium either. Then 1 will have a profitable deviation, because if T1 is equal to T2, firm 1 will choose a price just equal to T2, a time just equal to T2 and get the entire market. So, that is the idea. So, there cannot be an equilibrium in this case. Briefly describe the second price sealed bid auction. Okay. Second price sealed bid auction. Players and bidders, actions, possible bids, non-negative numbers, and preferences. If Bi is greater than B bar, where B bar is the highest bid of other players, then payoff of player I is equal to Vi minus B bar. Also, if Bi is equal to B bar, but I is less than J, where J is bidding B bar, then Ui is same, that is Vi minus B bar, otherwise 0. Thank you.